Welcome. Today we're going to be looking at the solar system data table found toward the back end of your Earth Science reference table. You'll notice there's a tremendous amount of free information just posted here within this data table. We've got the celestial objects starting with the Sun at the center of our solar system, and then each of the 8 planets are listed in order based on distance from the Sun. You'll notice also at the end that they have tagged on Earth's moon. I always like to put a separating line here, just as a reminder that Earth's moon is not the 9th farthest object from the Sun, but they do kind of just add that information about Earth's moon on at the end of the chart. So listed in order, we've got Mercury, Venus, Earth, and Mars. These 4 planets are referred to as the inner planets, also known as the terrestrial or rocky planets. Then we've got the 4 outer planets, which would be Jupiter, Saturn, Uranus, and Neptune. These 4 outer planets are referred to as the Jovian planets, or the gas giants. Sitting in between Mars and Jupiter, separating the inners from the outers, you would find the asteroid belt. So let's take a closer look at the information they're giving us here. We've got the mean distance from the Sun in millions of kilometers, period of revolution. Remember, a period of revolution is what defines a year on a planet. And the period of rotation, spinning on its axis, is what defines a quote-unquote day on a planet. Eccentricity of orbit. Let's take a moment to refresh our memory on eccentricity. Remember, eccentricity is the shape of a planet's orbit as it goes around the Sun. Eccentricity can have a maximum value of 1, which means your orbital shape is more linear, or a minimum eccentricity of 0, which would mean your orbital shape is more circular. Equatorial diameter in kilometers is literally just the measurement of the size of the planet along the equatorial diameter. That's in kilometers if I said miles. Mass is basically the mass of the planet compared to Earth. We set Earth equal to 1, and then all of the other numbers are relative comparisons to the mass of Earth. Density, finally, in grams per cubic centimeter. You'll notice that Earth happens to be the most dense planet in our solar system. So the types of questions you could be asked. A couple of brief review questions. How long is a year on Jupiter? So let's see. How long is a year? I know year is based on period of revolution. Jupiter is here. These two intersect at 11.9 years. Remember, we're always going to define units of time based on the units of time that we use here on Earth. Weeks, days, months, years, so on and so forth. How long is a day on Saturn? So a day is based on period of revolution. Saturn sits here. A day on Saturn lasts 10 hours and 14 minutes to be exact. Let's now go look at a couple of sample questions that you might see on a test or a quiz. Which object in our solar system has the greatest density? We actually just talked about that. The greatest density, very easy. I go to my density column, which is here, and the largest number, once again, belongs to Earth. So when I bounce back to my question, it looks like choice B would be the way to go. Another sample question. Which planet's orbit around the Sun is most nearly circular? Most nearly circular. This is based on eccentricity. Remember, closer to 0 means I'm more zero-ish or circular in shape. So my choices are Mercury, Neptune, Pluto, and Venus. Keep in mind, I picked this question just to show you that there are older questions out there that will sometimes refer to Pluto as a choice. We know that Pluto is not found on the solar system data table any longer, so anytime you see Pluto as a choice, you can just automatically disregard it. So really my possibilities are Mercury, Neptune, and Venus. Closest to 0, Mercury, Neptune, Venus. Let's see, here's my eccentricity. Here's Mercury, here's Venus, here's Neptune. Which one of those is closer to 0? Well, it looks to me like Venus has the lowest eccentricity value. So that means Venus would have a more circular orbit around the Sun. Choice D, Venus, way to go. Another sample question. The terrestrial planets differ from the Jovian planets because the terrestrial planets are, and then it looks like they want me to consider density and size. So let's bounce back to the reference table and check out my density and size. I'm just going to clean it up a little bit for consideration. Density and size with differences between the Jovian and the terrestrial planets. So let's see. My densities sit here. The 4 terrestrial planets have densities ranging from 3.9 to 5.5. My Jovian planets have densities ranging from 0.7 to 1.8. So it seems very evident that my terrestrial planets are more dense. Let's now look at size. My terrestrial planets have equatorial diameters in the range of maybe 5,000 to 12,000, where my Jovian planets are much larger in size, ranging from the smallest at 49,000 all the way up to 142,000 and change. So it looks to me like the terrestrial planets are more dense and smaller in size. Let's go look at our choices. More dense and smaller in size. Here we go, choice D. Excellent. Let's do one last question. Actually, that was the last question. I take it back. I hope this has been a helpful review on the solar system data table and that you have found it of some assistance. Thank you so much.